I'm just going to give a brief overview of some of the key points of the science. As Kevin said, I can't hope to cover the whole subject area, so if you want more details, the references he quoted are some of the places to go to, particularly IPCC columns. This just shows a plot of what we know about CO2 for the last 10,000 years. This is, This is a record going back 10,000 years, and you see that the CO2's hovered just between about 280 to 270 ppm. And just look at it, that's what was done recently. So clearly, it stands out a clear spike. This increase we can correlate very well with the onset of the use of fossil fuels, coal, oil, and gas. And actually, the quantities of CO2 released from burning fossil fuels correspond to this spike. Just to show you what a problem we have, if we look at the last recent 20 or 30 years here, the problem we are now facing is that the rate of CO2 is increasing even faster. This shows that in 1970 we were increasing about 1 ppm per year. Now we are increasing about 2 parts per million per year. So that very rapid spike's getting even sharper. It's a serious issue. Where's the CO2? Where's carbon sitting? This is just a very brief overview. The key point is most of the carbon is sitting, and CO2 is sitting in the oceans. It's the gorilla on the Earth, if you like. The atmosphere is responding to emissions that we are now doing, but eventually the oceans will take care of it. We don't have to worry. But we do. The reason we have to be concerned is that to get the CO2 from the atmosphere, it's continually exchanging with the ocean. To exchange it with the surface oceans may only take several years, but to actually bury it in the deep oceans can take 1,000 years. So this pulse of CO2 that we're now putting in will take at least 1,000 to 2,000 years to get dissipated into the oceans. And eventually, of course, it'll get buried in ocean sediments, but that'll take millions of years. So the whole problem then is the disequilibrium between the atmosphere and the oceans. This is just, again, a highlight of some of what Hansen was saying and shown by Kevin. This is some of the key factors driving our warming. Here's the atmospheric CO2 increasing. There are some reverse forcing, if you like. For example, this blue curve shows the effect of volcanic emissions into the stratosphere. So when volcanoes go off, we can't tell when they go off. We can't predict volcanic eruptions that accurately yet. They cause a negative spike because some of the solar radiation is then reflected back up into the atmosphere. This event, for example, was the Manitoba eruption. So when we look at then the record of Earth temperature, we do of course have some variability, and this just shows the actual observations in the blue, and these are the various models. And once you allow for the volcanic eruption, you can actually predict quite well some of these spikes. And also there's things like some El Nino events that are causing some variability as well. We don't think that solar variability shown here is a trivial amount of the whole course. The other point to see is that from about 1970 onwards, the CO2 we're emitting is becoming a clear dominant signal. So we're now on the part of the curve where we're now clearly seeing this forcing above all those more above the offsetting factors like e.g. volcanism. So the oceans, as I mentioned, are key in this. They actually absorb large proportions of CO2. I'll now go talk about this is showing already the temperature increase in the oceans. I'll talk a bit about this process called ocean acidification, which is actually a very simple process to understand, and also some consequences such as sea level. First though, what's actually happened with CO2 over even longer time periods? We have some excellent information from ice cores that goes back, this is 800,000 years and now almost 1 million years. And this is the well-known cycling of atmospheric CO2. Here we are today, about 280 ppm. And yes, there were some periods that were, these are warm periods. This is called the last interglacial. And we know it's warm from records from the ocean. So there is a coincidence in a very broad sense between CO2 and warming. Now I'll point out though that the scale here, this is 280 ppm. So today we're up here, so we're outside the natural range of CO2 for at least 800,000 years. And if you go back, it's at least 50 million years before we even have a glimpse of an event like what we're now seeing today. What's causing this fluctuation? Well, it's well known that the amount of solar radiation received by the Earth depends on its orbit, in part because the axis of the Earth is tilted relative to the plane of the ecliptic. This is called orbital forcing, and it was known by this guy Milankovitch some time ago. And he predicted that because of the abundance of the continents in the northern hemisphere, that these cycles follow when the radiation received in the northern hemisphere is at a maximum. That then tends to drive the Earth into these cold, warm phases. What about the relationship that we know in the past between CO2 and temperature? We can actually go to the ice cores again. This is from the Antarctic. And you can actually measure the concentration of CO2 in the gas bubbles. And this is shown by this black curve here. And this is an isotope measurement of deuterium, which actually reflects, we think, mainly temperature. The very first order thing is that you see that the very close correspondence between CO2 and temperature. These almost lay on top of each other, but not quite. The reason why they don't quite is because what's happening is that we have this change of the radiation received by the Earth is changing because of the change in its orbit, the so-called orbital theory. And there is periods when warming starts to increase in the northern hemisphere. That starts about here. So the Earth starts to warm, and the temperature is driving the effect. And this then is causing a series of feedback loops. It warms, as I said, not uniformly, more in the northern hemisphere. Then CO2, as you know, if you start warming a liquid, CO2 will start to be released. That then causes a feedback loop, it causes more warming. The rising levels cause more warming, and then, so what's happening, this is shown here, the insulation is rising, actually temperature is leading CO2. Actually, there's a very interesting part here where the warming temporarily ceases. This is called the Antarctic cold reversal. Actually, we still don't have a clear idea what it is, but it's probably, some of the ice is much harder to melt in some parts than the others. And you can see here that this actually was a period of slightly declining temperatures and stable CO2. Actually, to me, I looked at it, it will actually provide some hope. If we can actually get our CO2 levels to stabilise, as happened in the past for short periods, then that could well start to drive temperatures down, just from a very simple observation. And then the last part of the glacial or deglaciation occurred at about 10,000 years, and this is when the insulation in the northern hemisphere reached the maximum and then started to decline. The CO2 and temperatures in CO2 have since been stable for that last 10,000 years, which was the very first slide I showed you. So it's not surprising, in fact, that in the geologic record, for many parts of it, such as here, that temperature can lead CO2. We don't know a mechanism in the geologic record that can cause pulses of CO2 to come out roughly every 100,000 years. It just doesn't happen. Occasionally there are big volcanic events that we know about, in the Permian, Triassic, for example, some well-known events, but they're quite rare that volcanism itself drives climate. Now the simple effect of this ocean acidification is that most of it's an area of research I'm working on. We're quite interested in this. And what it is that as we increase CO2 in the atmosphere, as I mentioned, some is dissolving in seawater. And this is a very simple chemical effect. CO2 dissolves in water, making a fizzy drink of the surface oceans, essentially. And this is causing some changes in the seawater chemistry. I won't try and explain them all, but they involve making of calcium carbonate through the carbonate ion system. And what's happening is that the pH of the surface oceans is decreasing. It's heading in a more acidic direction. And in fact, this shows if we actually were so extravagant as to burn all the CO2 that we could get our hands on and push CO2 levels up to several thousand ppm, we'd change the chemistry of initially the surface oceans and eventually right through the main oceans over time periods of thousands of years. We're already driving the pH shift is already about 1/10 of a pH unit less now than it used to be. This has serious consequences, in particular